Hi everybody, welcome back. I hope you're enjoying the day so far. Next up, we've got Wido. Wido's talking about KVM storage performance with IO uring. Over to you, Wido.
Okay, thank you, Giles. Thank you. So yeah, welcome to this virtual CloudStack conference. I'm going to talk a bit about KVM storage performance with IO uring. But before we go towards the IO uring and KVM, thanks to our sponsors for this event. Actually, CLouDIN, the company I work for, is also a sponsor. But thanks for the rest for making this event possible. So a bit of background about the company CLouDIN and CLouDinfra is a lot of people know you. You might know me from the CloudStack community, where I used to work for the company PC Extreme. Well, that company is now part of Total Web Hosting Solutions, which is a hosting company within Europe with multiple brands. And we have those brands spread out of the Netherlands, France, and Spain. But we actually build our infrastructure with open source software, with Apache CloudStack, a lot of Ceph underneath it, and IPv6. So you might find other talks from me about Ceph and CloudStack and IPv6 and CloudStack and all kinds of things. So you can look back at a few talks I gave on earlier conferences about using CloudStack with these kinds of things. But today we're going to be talking about some other stuff about performance. But yes, some numbers of what we do with the CLouDIN and our cloud deployment. So it's all Apache CloudStack, and we currently have locations in the Netherlands, in the vicinity of Amsterdam, and then Haarlem, which is actually a city close to Amsterdam. And we're now building a location in Spain, in Valencia. Underneath this all, we're using advanced networking with shared networks with BGP, VXLAN, and EVPN. There's also a talk about this. And we're not using the VPC feature. We all have shared networks, so all the VMs which we have will have public IPv4 and IPv6 addresses. So that's what we're doing. And to scale this out, we're actually using VXLAN. And then underneath, we're using Ceph storage, or from some other places, we're using the TrueNAS Enterprise, which is actually high available ZFS. Now, a few numbers you can read, the amount of virtual machines, physical hosts, memory, etc., etc. And we're currently using hypervisors with the AMD EPYC 64 cores, actually dual CPU, a terabyte of memory, and we're either using Dell or Supermicro. It depends on who can supply the fastest and who gives us the best quote. But these are currently the models which we're standardizing on and which we're buying for all our deployments. So that's about CLouDIN and a bit about me or what we do, but actually we're here to talk about performance of storage. So what we see is applications which we run as a hoster is that usually bare metal with NVMe drives gives you the best performance. You know, you get the lowest latency on the IOPS. Latency and IOPS are connected, because if you have a lower latency, you'll get more IOPS, because if an IO takes less time, then actually you can do more within the same second, because IOPS is actually input-output operations per second. But for flexibility, we want to run the workloads inside virtual machines. So yeah, then you start looking at virtual machines, but then we'll see that CPU memory has a small performance overhead. You can say about 5% if you use some benchmarks between bare metal and a virtual machine. Memory and CPU is usually not that much of a problem. However, disk I/O has a much higher overhead. And this can become a problem for applications which really depend on I/O performance. So yeah, how do we fix it? And then looking at KVM, we have the QCOW2 format. So if you're using CloudStack with either local storage or NFS as primary storage, you'll see that it's actually using the QCOW2 files for storing the data of the virtual machines. And this is all being handled by the virt.io block driver inside KVM and QEMU, which is converting the IOPS from the virtual machine towards the host. But one thing you need to know is that IOPS are expensive. Everybody talks about that storage is expensive, but that's not really true. Gigabytes, terabytes, and petabytes, those are cheap. You can, I recently saw a news outing that there was the 22 terabyte drive. I think that's the newest drive you can buy. Getting terabytes of storage is fairly cheap, but IOPS are expensive. So if you can save on IOPS, do that. So that's applications, try to use as less IOPS as possible, because otherwise you need to invest in more and expensive and faster hardware to get these IOPS. But then you say, well, I really need the IOPS. How do I get there? Well, this is why we have IO uring. This is a new mapping between the host and the hypervisor and the virtual machine. And this provides lower latency and thus more IOPS. So let me get back again to IOPS and latency, because they are connected. Let's say I have a latency of 1 millisecond. X amount of IOPS within that second, because a second is 1,000 milliseconds. So my IOP will be 1 millisecond. I can do 1,000 IOPS. 0.1 milliseconds, I can do 10,000 IOPS within the same second. So if you reduce the latency, you get more IOPS. And then we're talking about using a queue depth of 1, of course. If you're starting to using higher queue depths of 4, 8, 16, 32, you'll get more IOPS, but usually it's the latency of the single IO, which is very important. And for an example, we host a lot of websites, e-commerce websites using Magento. Many of you might know it. This is an e-commerce platform, but it's really IO hungry. But what we also know is that conversion in web shops goes up if the page load of a website goes down. And there's actually been some investigations that if you lower the response time of a website by 100 milliseconds, we as humans notice it and we're more inclined to buy on a specific web shop because it has a lower page load. So we want to run these applications, the e-commerce applications, inside virtual machines, but at the moment, the latency of the IOs inside KVM are too high to actually run a e-commerce website with Magento, which is really busy. So we still have some bare metal running out there where we have e-commerce websites, but it's not the flexibility which we want. If something goes wrong with the hardware, we need to go there, fix it. It takes a lot more time. So we want to get this into virtual machines, and most of the workloads we have actually running VMs, but not all of them. But still, the other VMs which we have would also benefit from having more IOPS. So that's where IO uring can help us. Again, this is a new mapping between the host, the hypervisor, and then the virtual machine. Well, and the software requirements, it's nowadays available with the latest kernel and with QEMU and libvirt. If you're using CentOS 8 or Elma Linux 8 or Ubuntu 20.04, it's actually not available yet. You'll need to be using Ubuntu 22.04. So before we go actually to performance benchmarks, there's one more thing you need to know about the disk formats. QCOW2, as I said, being used by local storage and NFS primary storage is a very flexible format. It allows snapshotting, cloning of volumes. It also allows shrinking of volumes, resizing, growing of volumes. It supports the trimming. So if you do an FS trim inside the VM, the QCOW file will actually shrink and give back the free space to either your local or your NFS storage. So it's a very flexible format. However, it's not the fastest. If you're using raw block devices, those are the fastest, but it's not being used that much, and you also be consuming all the space you allocate will be consumed on either your local or NFS storage if you're using raw devices. So most of them are using the QCOW2 format. But then if you want to have some more performance with QCOW2, there's something you can do which is called QCOW2 pre-allocation. And I just copied this from my website somewhere, so I didn't type this myself. I think it's actually on Wikipedia, but there are a few pre-allocation methods. So there's the metadata pre-allocation, the falloc, and then there's the full. Well, as you can see here in the text, actually the falloc or the falloc method is the one which you should choose in most cases. It will allocate the space for the metadata and the data, but marks them as unallocated. And what you will see is that the performance of the QCOW2 file will become better and better after you have written more data to it, because the file starts growing. And then actually, if you write to a block which you initially wrote to it, well, it doesn't need to grow anymore, you'll get better performance. But if you do not allocate anything, you'll see that the QCOW2 file has a much lower IO performance than one which you did pre-allocate. And CloudStack actually supports pre-allocation, so that is a good thing. By the way, in the meantime, I actually have the chat open here if there are any questions. I don't see any questions yet. If you have any questions about the slides, do ask them in the chat, because I have the chat open next to me so I can answer questions. We don't need to save them to the last part. That said, I did some testing with IO uring and QCOW2. So I took one of the machines which we have. This is actually not a hypervisor, because you see this is a 16-core one, and we're using the dual 64-core for a hypervisor, but we had this machine available for testing for a while. So I just took a bare metal machine, installed Ubuntu, a single NVMe drive, so no RAID, just the ext4 file system, Ubuntu 20.04, but then I installed kernel 5.13, which through the hardware enablement, and from a PPA, I installed a QEMU 5.0 with also a newer libvirt, so IO uring would be supported. And I took a manual libvirt with a manual XML file to deploy the VM. I didn't test it with CloudStack because the results will be the same in the end, but it was easier for me so I could have one disk attached with IO uring, one without, etc., etc. It made testing for me easier. And then I deployed a single VM with 16 cores, 64 gigs of memory, and also Ubuntu 20.04 with a recent kernel. And then everybody's looking into, okay, results, what does it bring us? So I did some fairly simple tests because I just want to measure latency in a single queue depth. So if a queue depth of 1. So I took the command dd, wrote blocks of 512 bytes, 1,000 of them, called the flag desync, so it should all be written persistent to the storage, and then if you get a lower number, it's better. So here we see in the green one, which one is actually the hypervisor. So on bare metal, this would finish within 0.1 second. Now, if we're looking at the raw format or the QCOW file using IO uring, you see that the performance is, well, it's less, it takes more time. But if you're looking completely to the right, where we see the QCOW2 sparse file, which is not using IO uring, it's 6 times as slow as you would using bare metal. So going towards a QCOW2, either using the FAT or the sparse allocation, you already win a lot of time and your performance goes up with about 50%, depending on what you're using. And also you can see here the TrueNAS system, which I benchmarked, which is over NFS, over a 100 gig line, is about as fast as the local storage would be with a QCOW2 file. And why? Because the latency inside VirtIO block inside KVM takes so much time that the latency the network then actually adds is not that much anymore for that TrueNAS system. I didn't expect these results. I would have expected the TrueNAS system to be slower, but it was actually very fast on writing these IOs. And I was a bit surprised that the local storage would be that slow without using IO uring. Some other testing with FIO Simple 4K writes, queue depth of 1, and then the amount of IOPS you could get in the same time. Well, here we see again a bare metal machine gets 45,000 IOPS, but there we see that the QCOW2 sparse without IO uring is about 10,000 IOPS, and actually the TrueNAS performed better here. I ran these benchmarks a couple of times. I'm not really sure why, but you could say that both are equal on performance, about 10 to 11,000 IOPS. But what we do see is that the raw format and the QCOW2 with the FAT allocation, they double the amount of IOPS you can get compared to not using IO uring. And this is a real game changer because you get the double the amount of IOPS inside the same VM. And the NVMe in the hypervisor has the performance available, so why not use it? Because otherwise you'll just be wasting CPU cycles and waiting on a slow translation between the virtual machine and the block device. Now, I also found some results on the internet, and this is actually then an open question for the community, because I was looking at some other results, and here you see that people say that they get almost about the same performance as bare metal. And I tried a lot of things getting to the same results, but I was not able to get the same results. I was tuning libvirt, I was using the raw format, all kinds of stuff to get to the near bare metal performance. I didn't succeed in getting the near bare metal performance. So this is an open question to the community. If anybody knows the answer on how to get to these performance results, I'd like to know, because I want to improve there as well. So I think it would be good feedback for the community to see how we can get to this. So further testing is needed, but what we do see here in the previous results, we make a huge jump going from about 11,000 IOPS to, let's say, 26,000 IOPS on the same machine, same hardware, just by using a different piece of software. So CloudStack and IO uring. It's supported since version 4.16, and it's enabled automatically if supported by libvirt and QEMU. On the bottom part of the slide, you'll see the if statement. It checks if there's a QEMU version and libvirt if they support, and if so, then the disk, the IO driver inside the disk definition is set to IO uring. And I see a question of Valentin. Is it possible to, because of the specific hardware and operating system? Well, I think he refers back to the previous slide. Valentin, I don't know. It could be hardware, it could be software, I don't know, but further testing is just needed to get here. If anybody has an idea and has feedback about it, please let me know, or actually let the user list below so that we can all learn from it and try to see how we can get as much out of KVM as possible. But going back to CloudStack, the service offerings, they support different provisioning types. So you can either say what CloudStack, do you want thin, sparse, or fat provisioning? And this translates to thin. That means only the metadata is allocated. This is actually the default thin provisioning. Usually then when creating a service offering or a disk offering, because the service offering is the root disk and a disk offering is the data disk, then you use it to sparse or to fat. I think that in most cases, sparse allocation is fine to use, although fat is a bit faster. I don't think that because you'll be pre-allocating all the space on your file system already underneath on the hypervisor or on your primary storage. I think that sparse allocation by using Veloc is sufficient. You'll still get the performance benefits, but you're not consuming all the space. So keep in mind when creating a disk offering or a service offering and you want to get the high performance, make sure you use a sparse allocation for CloudStack. So what I did in libvirt with my manual testing, this is just a snippet of the XML file. I set the IO threads to 16 and CloudStack should already do this, but then also underneath the driver, it sets IO equals IO uring. That's the only change you need to make to enable IO uring. And CloudStack does this because in the code it checks, and then go back to this if statement. It says disk set IO driver, and then it will set it to IO uring. There's also native and threads, but we're not doing anything with that. We're just setting it to IO uring. Also with the testing, you need to use the virt.io SCSI driver. And that's something you set by using the proper operating system in CloudStack, using, for example, other Linux, and then I think it's called PV SCSI or something. But then I will choose the virt.io SCSI driver and you'll get the SCSI devices inside your VM. And what you see with the testing, this is actually a disk SDC attached, and I used SDA for the root of this VM, SDB, SDC, SDD. I just attached all kinds of different disks to the VM and then ran my benchmarks on it. Yeah, okay. I just saw some chat coming by from Gabriel. We'll get to that in a second. So my conclusion is that still that virt.io block seems to be the limiting factor currently, because local storage should and can be much faster than right now. IO uring already lowers the latency about 50%, so we'll get double the performance with IO uring than we would have. But the other benchmarks, they suggest that we should get 80 to 90% of the bare metal performance inside the VM. And I still need to investigate, but again, I'm reaching out to community, to others to also investigate and do these performance testing, so that we might need to change a few things in the XML of libvirt or some tuning for KVM settings. I don't know, but we should be able to get to the same bare metal performance, and then I'll go back to these benchmarks. These were actually false and there was a mistake in these benchmarks. I don't know. I trust Phoronix because they usually have very good results. But again, I was not able to get to the 45,000 IOPS I get in my hypervisor, and I'm stuck at about 26 to 27,000 IOPS. I would like to get to about, let's say, 35 to 40,000 IOPS inside the VM, because then the latency is lower and we can probably run the e-commerce applications inside VMs. I do think that with the 50% lower latency, we should be able to run the e-commerce applications in there. But yeah, more IOPS is better, and especially if you have the hardware available, which can already provide it. And then I see a good answer from Benko that the IO uring pass-through is not the same as IO uring in QEMU. And that's an interesting part, because I saw people on Twitter as well doing benchmark with FIO connected via the IO uring and also with QEMU. So there's all kinds of results going around there, and I would like to get to a conclusive answer. So maybe, Benko, we can start a conversation on the users mailing list or the dev mailing list and actually talk about this to come to a definitive answer on how we can get this performance better, because now with 4.16, there's IO uring available, and we can do more if we want. Okay, that was the conclusion. But looking forward, so it's supported in CloudStack 4.16 and Ubuntu 22.04 LTS called Jammy has all the packages available. So QEMU 6.3 and libvirt 8 is available. Again, more performance testing and more real life experience are welcome. It might be that we need to do a few enhancements to the XML. So we can do this in the Java code of CloudStack, but there's also the libvirt hooks. And this is an interesting part you could use for all kinds of stuff. When CloudStack defines the XML inside libvirt, it actually can call a hook where you could still manually modify the XML file before it starts the VM. So that's an interesting part where you could say with hooks, you can change all kinds of stuff to the XML of libvirt before the VM is started, which could be some modifications you need in your local environment. And then if we have any questions, you can find me on Twitter or my private email address. But again, I would like to have the feedback go to the users mailing list, because then we can all benefit and we can share and we can respond to it. So it will go into the archives and people can learn from it. But I do see that Venko, indeed, he is bringing some good stuff into the chat. True, Venko. Yeah, I was talking about the raw format because Venko says that raw versus QCOW. Raw does not necessarily mean you're missing features like snapshots. That is true, indeed. Depends on your storage system. But if you just be looking at local storage and where QEMU can create a snapshot, for example, that is not really possible with the raw format. Of course, a Ceph RBD uses the raw format. I know that Storepool uses raw and that the storage platform then provides the snapshotting. But if looking at basics, if you're just creating a file with QEMU, it will be either a raw file or a QCOW2 file, and you don't have all the features available. So that's something to look into. When these slides are being shared, I have an appendix with a few links in there where I got my information from. So we have a few things about the raw versus QCOW and the QCOW disk performance. And also, I think there's a link here. So IO uring is mentioned here as well. So something to look into. Okay, if that was mainly my talk about IO uring, any further questions which might appear in the chat, I'll wait for those. And actually, John, I told you I don't need the 40 minutes. You know, about 30 minutes should be sufficient.
You did, Wido. You did.
Yeah.
I think it gives everybody a chance to get a late lunch or something. Any more questions for Wido in the chat?
I see thumbs going up for Venko, so that's a good thing.
It's one of the annoying things. This events platform is great, but one of the annoying things is we can't actually bring people. I would have brought Venko into this call and let you guys have a chat.
That would be great.
I can't do that, unfortunately. It's chat or nothing. Sorry, Venko.
Yeah. Yeah. Yeah, so indeed, because indeed Rohit has some, of course, if you're using Scale.io, he says, yeah, you can also have external snapshots, all kinds of stuff you can do with external stuff. And I know you're completely right that if you have some external things outside CloudStack, but in the basics, the raw or the QCOW format, they have a bit of differences, but we can all kind of fancy things, BTRFS on the local storage and do snapshotting there, or using ZFS underneath it. All kinds of things where you could do snapshotting, but QCOW2 has the possibility inside the format itself. Okay.
Okay.
I see Yvette. Yeah, you're welcome for the talk. If there are any other questions, do let me know. Indeed, Venko and we can catch up in the lounge, as Yvette says in the chat. Brilliant. If there are no further questions, then I would say, everybody, thank you.
So as
watching.
As Wido says, he's going to go and hang in one of the lounges. There's his contact details if you've got any follow-up questions. Thank you very much, Wido.
You're welcome.